Uh, Welcome, esteemed colleagues and guests. This is Mustafa Istanbullu. I'm working as an assistant professor in the biomedical engineering department and at Çukurova University in Turkey. I am honored to present our research titled Correlation-Based Adaptive Multimodal Fusion Approach for Continuous Driver Fatigue Monitoring. As you can see on our title slide, driving involves a chaotic interplay of physiological signals, heart rates, oxygen levels, and skin conductance. Our primary objective today is to show you how we synthesize this chaotic biological data into a single predictive safety metrics. This is the fatigue trend score. Rather than waiting for a driver to make a critical error, we are monitoring their physiological state continuously to ensure safety. I want to draw your attention to the quote on the screen, the invisible descent into fatigue. Driver fatigue is a leading silent cause of traffic accidents, especially during long monotonous drives. The keyword here is invisible. Fatigue is not a sudden switch that turns off the brain. It's gradual physiological degradation. Therefore, our goal as engineers and researchers is no longer just detecting a sleeping driver whose eyes are already closed. Our goal must be monitoring this invisible descent into fatigue long before it becomes visually apparent. To understand where our research fits in, let's look at the three main fatigue detection paradigms currently in use. First one on the left, we have vehicle-based systems that track lane geometry and steering dynamics. These are highly susceptible to road conditions, weather, and traffic density. Second, in the middle, we have behavioral-based systems tracking blinking rate and head tilt via cameras. These fail in poor lighting, obscured angles, or simply if the driver wears certain glasses. Notice the warning labels at the bottom. Both of these are strictly reactive and event-based. On the right is the current physiological paradigm. While tracking EEG and ECG is highly accurate, it has historically required clinical patches or headgear, making it obtrusive and unsustainable for daily driving. Our approach takes this physiological pillar and transforms it into a continuous early warning fatigue trend score without these discomforts. We must monitor the autonomic nervous system before the event occurs. Let's compare the two graphs on this slide. On the left, reactive event detection shows a system waiting for observable failures like eyes closing or abrupt braking. As the red graph violently crashes down, the damage is often already done. On the right, predictive physiological monitoring shows a completely different philosophy. By tracking internal biological shifts, the blue or green trend line reveals the invisible descent into fatigue early. It catches the physiological drift long before the driver reaches the critical failure point. However, this brings us to a significant hurdle, the dimensionality problem of multimodal data. Combining multiple physiological signals like heart rate, skin conductance, and oxygen levels drastically increase accuracy. But at the same time, of course, it creates a massive data bottleneck and a tangled multidimensional chaos. The core research question of our study is exactly this. How do we fuse this multidimensional chaos into an interpretable output without overwhelming the system's computational limits? Before we solve the data chaos, we must solve the physical hardware problem. As shown here, we are eliminating clinical patches entirely through the driver's natural driving posture. We engineered a steering wheel with three specific sensor zones. Zone 1 focuses on the left and right palms, where an AD8232 analog front end captures a single channel ECG continuously through these conductive electrodes. Zone 2 incorporates finger contact zones, where a groove sensor, GCR sensor, tracks electrodermal activity via the natural driving grip. Finally, Zone 3 utilizes optical sensors, specifically a MAX 30100 to calculate peripheral oxygen saturation via red and infrared light. The driver just simply holds the wheel. From the steering wheel, we extract specific features from our multimodal physiological sensor sheet. From the ECG, we extract the heart rate, HR, the standard deviation of NN intervals from the ECG signal, the root mean square of successive differences, this is RMSSD, and the low-high frequency ratio. These heart rate variable metrics give us a detailed view of sympathetic balance. From the galvanic skin response, we extract the skin conductance level. This is the SCL, which represents the baseline tonic sympathetic arousal, and the skin conductance response. This is the SCR, representing rapid phasic bursts. Lastly, we extract oxygen saturation from the peripheral optical data. To process these distinct biological signals, we built a rigorous synchronization and normalization pipeline mapped out in 4 stages on the screen. First, analog input is captured directly from the steering wheel sensors. Second is digitization, managed by an Atmega 328P with a 10-bit analog to digital converter, targeting a 500 Hz sampling frequency to capture precious cardiac RPEs. Third is time alignment. Since we are dealing with asynchronous biological events, our Python multi-threaded collection uses high-resolution timestamps to dynamically handle latency. Finally, minimum maximum normalization scales all these heterogeneous biological data to a uniform 0 to 1 range. Crucially, we apply a 1 minus x inversion for decreasing vectors like heart rate. So all metrics align directionally with increasing fatigue. Now, how do we combine these normalized signals? On the left, you see a broken scale representing static weighting. Physiological responses to fatigue vary significantly across different individuals and even across different driving sessions for the same person. Rigid, static weights simply break under natural biological variance. On the right is our solution. It is adaptive weighting. the system must adapt dynamically to the intrinsic relationships within the data. It must balance the influence of ECG, GCR, or oxygen saturation in real time based on how strongly they correlate with the driver's actual physiological drift. Let's look at the mathematics behind this. Broken down into steps, in process 1, we establish a baseline. As the equation solves, score 0 is a temporary combined score calculating using initial baseline weights. These are VIs, multiplied by the normalized inputs. These are the XIs. Once we have the baseline reference, we move to process 2. This is the Pearson correlation. Here we calculate the correlation coefficients, RIs, between each individual physiological parameter XI and the overall trend of that temporary score. This tells us exactly which signal are currently driving the fatigue trend. Moving to the final mathematical steps, in process 3, we generate the dynamic weights. We take the absolute correlation values we just calculated and convert them into adaptive weights. As illustrated by the weighting funnel, highly correlated features gain massive influence, while weak, noisy signals are mathematically minimized. Finally, in process 4, we calculate the continuous fatigue trend score, or FTS. We call them FTS. We sum the dynamically weighted features to create a single normalized 0 to 1 predictive safety metric, FTS. To prove this architecture works, we conducted experimental validation in a control simulator. As depicted here, data was collected using a PlayStation-based driving simulation environment paired with a custom-modified Logitech G29 steering wheel module. This setup allowed for the safe capture of naturalistic multi-channel physiological response over prolonged, highly monotonous driving sessions. The raw ECG, GCR, and SpO2 signals flow from the wheel directly into our data processing terminal for data convergence. The data we collected revealed fascinating hidden relationships, which you can see in this correlation matrix. Look specifically at the FTS row highlighted at the bottom. The matrix proves variables relate completely different to fatigue progression. For example, we see strong positive correlation for STNN. This is 0.85. And RMSSD this is the 0.84, but a negative correlation for heart rate, it's minus 0.49. This varying distribution empirically validates the absolute necessity of dynamic data-driven weighting over assuming equal signal contribution. If we used static weights, we should severely misinterpret the driver's state. When our algorithm dynamically processes these correlations, it generates the contribution donut chart you see here. The algorithm dynamically determined that heart rate variability and galvanic skin response components carry the most significant predictive weight for fatigue. Specifically, SDNN and RMSSD both commanded high adaptive weights of 0.0 243. Heart rate contributed 0.155, while the tonic skin conductance level SCL contributed 0.136, followed by the phasic SCR at 0.111. Peripheral oxygen had the lowest predictive weight at 0.022, acting mostly as a baseline physiological monitor. When we apply these adaptive weights continuously, we generate the continuous fatigue trend score graph shown here, recorded over a 2-hour driving session. The thin gray line represents the raw FTS, which naturally contains short-term physiological noise. However, by applying 20 sample moving average to this graph, represented by the thick glowing yellow line, we remove that noise. What is revealed is a clear, undeniable, and upward trending narrative of the driver's descent into fatigue. As time progresses from 3:30 p.m. to 5:30 p.m., the score steadily climbs towards 1, giving the system ample time to intervene. Why does this unified FTS metric change the game? For 3 distinct reasons, of course. First one is the dimensionality reduction. We successfully transform an uninterpretable multidimensional biological space into a compact one-dimensional continuous signal. Second, low computational complexity, because we use adaptive weighting rather than massive multi-input neural networks. The algorithm eliminates computational overhead, making it exceptionally viable for real-time edge applications. Third one is the predictive capability. It unlocks the maybe this is the most important one. It unlocks the ability to trigger intelligent, non-intrusive alerts before the driver reaches a critical accident-causing threshold. Looking ahead, our future horizons for real-world deployment involve moving this technology direct into the vehicle dashboard, as envisioned here. Our next step focus on embedded optimization, porting the algorithm to ultra-low power embedded hardware for immediate in-cabin edge computing. While we also conduct real road calibration, moving beyond simulators to account for environmental variables and individual driver baselines. Lastly, we will implement intelligent interventions by integrating the FTS graphs with fuzzy interference systems to create highly reliable state-based driver alert mechanisms. To conclude, our correlation-based adaptive multimodal fusion approach successfully reduces complex, separate physiological signals into a single, compact, and interpretable one-dimensional representation. Moving forward, we aim to optimize the computational load of this algorithm to integrate it directly into low-power embedded hardware for real-time operations. We also plan to develop individual driver calibration mechanisms, apply fuzzy interference systems for advanced classification, and ultimately validate our system in real-world vehicle environments. Furthermore, I am excited to announce that more detailed discussions and follow-up studies extended from this research will be presented at our upcoming workshop planned for late May. I think this was my last slide. Thank you for your listening. I provide my email address in the first slide, so if you want to ask anything, you can mail me. Thank you.